So, hello everyone. Today I will be presenting our research on mitigating information loss in text-independent speaker verification using Deep Information Maximizer. This project was actually our final year undergraduate research project, which I worked alongside Nipun. And we are guided by Dr. Buddhika and Dr. Udayasankar, and we are from Department of Computer Science and Engineering, University of Moratuwa. And before diving into our research, let me give a quick overview of text-independent speaker verification, how it works, and the previous research that inspired our work. So, speaker verification is a process of confirming speakers' claimed identity using their speech. In text-independent speaker verification is a special case, and in text-independent speaker verification, the system verifies the speaker's identity without being restricted to a specific speech content. And here's how most text-independent speaker verification systems work. First, we input speech signal and its speaker's identifier to the system, and the system extract the frame level features, which are low level feature maps. And these feature maps then go through a pooling layer to create a high level speaker embedding by aggregating multiple frame level feature maps. And then the system retrieves stored speaker embedding from its database and compare the two embeddings using similarity measure techniques such as cosine similarity or whatever. And if similarity exceed a certain threshold, speaker is verified. And let's talk about the issue of the information loss in when creating discriminative speaker embeddings. The problem occurs in pooling layers due to the compressive nature of the pooling. Valuable speaker information get lost while generating these embeddings. So this reduces the model's accuracy and reliability. In our research, we address this issue by using a method called Deep Information Maximizer, which was originally used to generate deep image representation back in 2019. DIM worked by estimating and maximizing mutual information and strengthening the link between the low level and high level features. So this helps to reduce the information loss and leads more accurate and reliable models. So the motivation behind this research project is enhance the robustness of the voice-based verification and making the system more secure and dependable. As you can see, so there are several real-world applications in this text-independent speaker verification, including fraud detection as a biometric verification method, and so on. So let me briefly show key studies from our literature review which inspired us to develop our solution. So first one is mutual information neural estimator. This introduced to estimate mutual information, and the second one is Deep Informax, as I previously mentioned. So, and the third one is this information preserving pooling. So this information preserving pooling method use mutual information neural estimator to maximize the mutual information in X-vector baseline systems. And final one is our baseline model, fine-tuning pre-trained ASR transformers. So here's our baseline model. This model is proposed by Junai Peng in 2022, and this model achieves the state-of-art performance during the time we are doing our literature review. And let me quickly explain two major components of this model. First one is ASR transformer. This automatic speech recognition transformer is used to effectively extract the features from encoded speech signals. And we have chosen Wave LM base plus because of its superior performance with the small size. And in the terms of layer usage, we are employing all 13 layers of this WLM base plus model as proposed by Junipen. And the topmost layers are particularly effective for capturing phonetic information, while the bottom and middle layers are good for capture speaker specific information. And this layered approach allows us to leverage strengthen of this ASR transformer and ensuring we can accurately process and understand the various speech inputs. And the second component is this pooling method. So here they propose multi-headed factorized attentive pooling. So each output of each layer of this ASR transformer are given to two types of attention weights. First one is key and attention weights, and second type is value attention weights. So key attention weights are basically responsible for capturing phonetic information, and the value stream is responsible for capturing discriminative speaker information. So to combine these information effectively, we apply softmax attention weights. So this process computes a weighted sum of the values based on their importance. So then resulting a final output more concise and ensures that the model emphasizes the most relevant information in the ASR output and improving the overall quality of the embeddings and accuracy of the speaker verification. So in our research, what we did was we introduced a regularization mechanism to maximize the mutual information of this final feature map of this ASR transformer and the final speaker embedding. So this discriminator estimate and maximize the mutual information, and we use two specific discriminators called local Infomax and global Infomax. So Deep Informax introduced this local and global information maximizers. And global information maximizer focuses on estimating and maximizing global mutual information, which helps to capture overall patterns of the data. And in contrast, local Infomax focuses to estimate and maximize the local mutual information, allowing to focus on frame level details within the data. So the main objective of global information maximize is capture the mutual information between frame level and high level information. So what here we did was to capture this, we need to create a negative pairs. So what we did was create we pick a different speakers feature map and concatenate it with this speaker's final embedding and create a fake score, and we concatenate the intermediate feature map and its own final embedding and create the positive score. So, and we did the same thing in local information maximizer as well, but one important thing was here we did frame-wise concatenation. So this enhanced the model's ability to focus on low frame level mutual information. That's why we frame-wise concatenated our final embeddings with the intermediate feature map. So we use junction and divergence as our objective function as described in the Deep Information paper. And our loss function has three terms: speaker classification loss, local and global mind objectives. And these alpha beta parameters controls the importance of local and global objectives of the final loss. And we use voxelab dataset for training, voxelab 1 dataset for training. So voxelab 1 dev test we use for training, and voxelab 1 test set for testing. And we use equal error rate as our evaluation metric. And we use 1D convolution layers for implementing both local informax and global informax, since we are dealing with the sequential data. And so here is our results. And we compared our results with baseline model, with dim integrated baseline model. So up to we did it with different attention heads. So up to 16th attention head, our proposed model got lower equal error rate compared to baseline model. And when it comes to hyperparameter tuning, we tried different alpha beta values, and for alpha equals 0.01 and beta equals 0.05, we got the best results. So the overall findings suggest that the increase in the number of attention heads generally leads the best performance, especially up to 16 head, where the dim integrated model surpassed our baseline. So additionally, the lower alpha beta values gives better results, and beta has a strong influence in the performance over alpha. And when it comes to our conclusion, we can say this Deep Informax can effectively reduce the information loss in text-independent speaker verification, and not only text-independent speaker verification, but also this can be used to mitigate information loss in several deep learning tasks. So thank you.